In this video, we're going to look at chapter 13 and gravitation. And gravity is something that we've talked about in the past, but we've only focused on Newtonian gravity. We're going to look at both Newtonian gravity and Einsteinian gravity. And we're also going to look at gravity in a slightly different sense. So a lot of it's going to be review, but pay attention because there are going to be a few little new tidbits peppered throughout. The gravitational force is responsible for a lot of things. For instance, it holds us to the Earth. It holds the Earth in orbit about the Sun. It holds the Sun together with the stars in our galaxy. It reaches across intergalactic space to hold together local groups of galaxies, and it holds together a local supercluster of galaxies. It puts the supercluster towards the great attractor, and it attempts to slow the expansion of the universe, even though the universe is still expanding. It's responsible for black holes, and it's a far-reaching and very important force. Oddly enough, it's actually the weakest of the four fundamental forces in the universe, but it's still a great force, and it's responsible for a lot. And we know that gravitational attraction depends upon the amount of stuff or the amount of matter that an object has. And because Earth has a lot of this stuff, it produces a large attraction. And the force is always attractive. We never repulse due to gravity. And we define gravity as the tendency for bodies to attract each other. So Newton was the first one to really start to conceptualize and quantify gravity. And he noticed this from looking at celestial bodies, and he figured out that gravity was the reason that they moved in the paths that they did. And so he quantified this relationship with the Newton's law of gravitation, and that defines the strength of this attraction. An example, we have about zero point 0.8 or just under 1 Newton for the attraction of an apple and the Earth, whereas the attraction between two people is less than 1 micronewton. We know Newton's universal law of gravity gives us this equation here where we have the two masses multiplied together by big G, the constant, which is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, and then we divide by the distance squared between the two. We can write this as a vector equation, just making our position vector, or saying that that's in the unit vector direction of the position, and so the force is going to attract between that position vector of the two centers. So we use this idea of the shell theorem, and this is the first time we're going to call it this. And it basically states that a uniform shell of matter attracts a particle that is outside of its shell as if the shell's mass were all concentrated at the center. And so this is how we deal with all point masses. We just say everything is at the center. And so we can view the Earth as a bunch of nesting shells. So we say all of Earth's mass is focused at the center. And as always, Newton's third law is going to apply here, and we have those action-reaction forces. And so the apple exerts a force on the Earth just as well as the Earth exerted a force on the apple. However, we notice two vastly different accelerations because of their individual masses. Through this video, for the sake of time, I am not going to discuss the checkpoints, but feel free to pause, read over the checkpoints, and look at the answers. Continuing here with gravity, we know that we can use the principle of superposition, which means we can sum all of the forces together using Newton's second law, and we can find the total gravitational force on an object due to multiple objects around it. And so if we have one object in the center here, and there's two other objects in its vicinity, then we can find the gravitational force on M1 due to M2 and M3 just by adding their two forces together, just like any two vectors. Now, when we're near the Earth's surface, we experience gravity, and we call that the acceleration due to gravity, and that's talking about our acceleration that we experience. And we know that's baby g, and we can find that using Newton's universal law of gravity and Newton's second law of the sum of the forces equal to mass times acceleration, and we can find the value for baby g using big G, mass of the Earth, and the radius of the Earth. And actually, this equation here can be used on any planet or any large body. We can look at the acceleration due to gravity of that body by using its mass and the distance to its center. And we know that this is approximately 9.8 meters per second squared. Now, if you look at this table over here of table 13.1, we see that that varies a little bit based on where we are. Now, this is the mean Earth surface. It's 9.83. We typically use 9.8. If you're on Mount Everest, you're going to be a little lower because you're higher up. You're farther away from the Earth's center. If you're at the highest crewed balloon, that's going to be 9.71. A space shuttle orbit, we're going to look at now, we're at 8.7 meters per second squared. And if you look at our communication satellites, they are in a much, much weaker gravitational field due to Earth because of their great distance, and that's 0.2 meters per second squared. Now, we make a lot of approximations like the Earth's spherical and uniform density and all that, but if we were to actually calculate and measure baby G all throughout the Earth at different locations, we're going to see that it varies a little bit. And there are three main reasons that it varies. The Earth's mass is not uniformly distributed. You can look at figure 13.5 to prove that to yourself. It's not a perfect sphere, and the Earth rotates. Let's talk about the rotation for a second here. Knowing that when something rotates, there is an acceleration. So if we look at an object that is sitting on a scale that's rotating because the Earth is rotating, then it has acceleration. So really, its normal force minus its weight is going to equal mass times that negative omega squared r. And we can calculate that, and we see that, you know what, the normal force is not equal to its weight. There's a slight difference, and baby G is not truly the acceleration due to gravity. It's the acceleration due to gravity minus the acceleration that is caused by the rotation. Now, on Earth, that is fairly negligible, even though our tangential velocity on the edge of the Earth is pretty fast. Remember, the Earth is huge, so our angular velocity is actually kind of small. It's like 7 times 10 to the negative fifth or something like that, radians per second. And then you square that, which is going to get really small. Now we're times 10 to the negative 10th, and then you multiply by the radius, even though that is big, but it's only on the magnitude of 10 to the 6th. So we're talking about, I think it's around 0.03 meters per second squared that this accounts for. So it's minute. However, it is there, and it is something that we do need to be aware of depending on the situation. Using this shell theorem, we're going to do a little thought experiment here. Now, obviously, this is not practical, and we could not conduct this experiment, but theoretically, let's say we bored a giant tunnel all the way from one end of the globe to the other. So let's say we go all the way from the North Pole to the South Pole, and there's this giant column that extends all the way through the Earth, and we just drop an object through there. Well, that object is going to fall towards the center of the Earth because gravity is exerting a force on it. But think about what's happening. As it goes towards the center, the mass that was once pulling it towards the center, well, now there's going to be some mass over here that's going to be pulling it in the opposite direction. So what do you think is going to happen to this mass as it's falling towards the center? Well, we can do a little math here to show us what's going to happen, but we can also think about it conceptually. Let's say, just for kicks here, that we're going to have a constant density throughout the Earth. Now, that is an approximation, but this is impractical anyway, so we can make those approximations. So we can say that the mass that's left, accounting for what we took out to make that column, divided by the volume is going to give us our density. So that's just m divided by 4/3 pi r cubed. That's about the mass of the Earth. We'll say that that column is pretty insignificant. And we know the force of attraction, or the force of gravity, is going to equal big G times the mass that we're dropping times the mass of the Earth times the radius divided by the radius cubed. Now, I'm not going to go into too much detail here of why it's like that, but just think about the distance that it is from the center. As it changes, you need to have that factored in, but you're smart enough, you can figure that out. And if we look at all of these constants, a lot of these are constants here, like this, all that stuff over there are constants, and that reduces our force down to a negative chunk of constants that we're just going to call k, times our position vector. Well, that looks oddly familiar. That looks a lot like Hooke's law. So this tells us that this object is going to oscillate through the Earth, back and forth and back and forth, and it would just be a never-ending pendulum. Now, big issue in this thought experiment, the Earth's rotation. If we were to actually try to do this, even if we could bore this tunnel, which is totally impossible, but let's say we could bore the tunnel, because of the Earth's rotation, that mass would not get very far, because as it would drop, it would run into the sides of the wall. So if we could get the Earth to stop, and if it didn't rotate, and we got this tunnel, then it would, in fact, oscillate back and forth and back and forth. And you'd be able to, if you jump from from the North Pole, you would come out on the South Pole, and you would just stop right at the surface of the Earth, and so you could, maybe grab onto something and jump off to the South Pole. So with gravity comes gravitational potential energy, and we've done this a bunch, conservation of energy from gravitational potential energy to kinetic energy. However, one little thing just to tell you that only works, and we never talked about this in AP Physics 1 because it never came up, but this is only true for systems where one object is much less massive than the other. So conservation of gravitational potential energy into kinetic energy, that's not always going to work when we, say, have two objects of equal mass. One has to be extremely more massive than the other for that to work. And we're going to say that the gravitational potential energy of a two-particle system, we're going to call it U, is equal to the negative of big G times the two masses divided by the distance between them. Now, this looks a lot like the force, but what's different here, we only have r in the denominator, not r squared. And so we see, well, force times distance is equal to the work, which is energy. Energy, you can make the connection, all right? So we're going to use this equation to look at the gravitational potential energy between any two-particle system. Now, what if we have three particles in a system, or 4, or 5, or 6? Well, we can use that same equation and just add together all the potentials for each individual pair of particles in that complex system. Now, one thing that I don't want you to get confused with what I said a few slides ago about how the conservation of gravitational potential energy and the kinetic energy only works when one mass is much, much larger than the other. Well, that doesn't mean that the force is not conservative. The gravitational force is always conservative. And so that means that the work done by this force does not depend on the path. It doesn't, it can just, all it depends upon are the starting points and the ending points and the difference in the positions. And so because of that, the change in potential energy is always going to equal the negative of the work done on the particle. And we've seen this with gravitational work. When the work we do to lift an object, that work is positive, so that means the change in the gravitational potential energy is going to be negative. Or vice versa, if the work is negative in lifting or lowering an object, then the change in potential energy is going to be positive. A couple neat things here that come about between energy and gravity, and calculus is kind of our vessel to connect the two. We can derive Newton's law of gravitation basically by looking at the potential energy and taking its derivative, which is kind of cool. And so just taking the derivative of the potential energy, that gives us Newton's law, universal law of gravity. And for a projectile object to escape the gravitational pull of a body, it must come to rest only at infinity. And so the idea of, well, it comes to rest at infinity, then we look at, well, r has to go off to infinity, and that's where u will equal 0. And if it's at rest at infinity, then k will equal 0. So that means k plus u must be at least 0 at the surface of the body. And so we do a little math, solve for v, knowing k is our 1/2 mv squared, u is our negative g mm over r, and we get the escape velocity on any planet is going to equal the square root of 2 times big G times the mass of that planet divided by the radius of the planet. And so when we launch rockets, we actually launch them eastward to take advantage of the Earth's rotational speed, so that way we can reach v, that special escape velocity v, a little more easily. So that rotational speed helps us reach the escape velocity. Table 13.2 here talks about the escape velocity of various different celestial bodies, whether they're going to be moons or planets or cold, icy dwarfs, like some of these things out here, or a neutron star, or the series, all that stuff out by Pluto. So they all have different escape velocities, and we can see those based on this table. With gravity, we also bring in Kepler's laws when we're talking about the planetary motion. And really nothing new here. Kepler's same old Kepler. So if you want to look up the history of the stuff, it's actually kind of interesting. He did kind of steal some of his ideas, but he gets a lot of credit, just like most scientists do. There are 3 of Kepler's laws that are important, and we actually still use Kepler's laws and Newton's laws to launch rockets out into space and deal with our satellites that are going around the Earth. So they're not completely antiquated. They are still useful. First law just basically states that we have elliptical orbits. Second law, we have the conservation of angular momentum, where we sweep out the same area for any time interval. And then third law is where we get the only math in Kepler's, where we have the ratio of the period squared over the radius squared of 2 different objects orbiting the same central object. Those are going to be constant, or those are going to be equal. And so they're equal to these constants here. And so from that, we get table 13.3 that gives us the periods for all of the planets, or whatever you want to call Pluto, in our solar system. So with a satellite, or an object that's orbiting a central object, we can relate the centripetal acceleration to the gravitational force. And when we do that, using our kinetic energy is equal to 1/2 mv squared, we basically get that the kinetic energy is equal to negative U/2, or it's half of our potential energy. And so that means the total the total mechanical energy of a satellite is going to be the kinetic plus the potential. And so when we add those together, we get a negative G m/2r. How this simplifies for us is that the total energy E is the negative of the kinetic energy. And so for an ellipse, we substitute A for R. And A, remember, is our semi-major axis distance. And so we actually don't depend on the eccentricity. And we just use A as our radius value. And so the unique thing here is that all these orbits pictured here have the same energies, even though they have very different eccentricities. So some are more elliptical than others. Their total energies are the same. And so finally, this lands us in Einstein's view of gravity. And we're not going to get into it too much in this video here, just a brief overview. Einstein came up with this idea of general relativity, the general theory of relativity. And it helps us describe gravity much more conclusively and fill in some of those holes and cracks that Newton had, and even Kepler had with his stuff. And so it basically redefines the way we look at gravity and how gravity works. And its fundamental postulate is the principle of equivalence. Now, what that means is that gravitation and acceleration are equivalent. And so we kind of use those equivocally at times, and it gets us confused at times, saying baby g is the acceleration due to gravity, but it's also gravity, but if we really get down to it, they are the same thing. And so a way to think of this is think of someone that's in a box, all right, and they're just going to drop a ball, and this person in the box drops a ball and observes the acceleration of that ball. So you're the person in the box, you drop it, you see it accelerate towards the floor. If you're on Earth, you see that acceleration to be 9.8 meters per second squared. Well, let's say that same person is in a box, but not on the Earth's surface, and it's in free space, and he happens to drop it and sees that it's also 9.8 meters per second squared. Well, that means that the gravity that each of these are experiencing are equivalent, but what's happening to these two people is very different. This person is stationary on the Earth's surface, where this person is flying through space, which gives him the perceived notion of gravity. And so what Einstein's saying is that's the same thing. That acceleration that you experience, that is gravity. There is no difference. And this is all based off of the fact that space and time are interwoven together into what we call the space-time continuum. And gravity is really the curvature of that space-time. And we'll talk a little more about this and what this means in class. And although this may sound a little screwy, we actually see evidence of this. We can see that light bends around extremely massive objects like black holes. We see evidence of the bending light, and we have what we call Einstein rings, and where we see a star in two different locations because of black holes between us and that star. And we've also even seen just recently gravity waves, and those are also proven in Einstein's theory of general relativity. And so we know that this stuff is true. It's a little crazy, but we know that it's true. One vocabulary thing here is gravitational lensing. That's where we get that effect when light bends around an extremely massive object and we can see double. There are some things that are still unclear about gravity in the world of physics today. The source of gravity itself is a little unclear. Is it purely an effect of curved space-time? Is it a force between masses? Is it due to a fundamental particle such as the graviton, which could carry a gravitational force? And so these questions are not yet answered. There's even more theories out there based on that. Now, what we are finding time and time again is that Einstein is still correct. And not that Newton was wrong. Newton was totally correct. Kepler was correct. Einstein is also correct. He is just finely tuned and more clearly defined what we think of as gravity, but there's still some questions that are left unanswered.